For centuries, the Swiss Alps stood as an imposing, frozen blockade, a colossal. By the late 20th century, the historic Gotthard Pass was overwhelmed. Millions of tons of cargo crawled over it. The Swiss population realized that seasonal roads and vulnerable mountain passes were no longer viable. They needed an app. In 1992, the Swiss public made a historic, democratic choice. Through a national referendum, with the legal and financial framework secured, Switzerland officially launched the Gotthard Base Tunnel project, a plan to drill a flat-level water bridge of steel under the mountains.
To align a tunnel 57 kilometers long from opposite ends had high
opulence. Before drilling the main tunnel, they had to build the infrastructure of access. They sank giant vertical shafts and drove
Thousands of miners and engineers from around the globe arrived in the Swiss valleys. They prepared to tunnel deep into the Alps, preparing for an epic mechanical clash with the mountain core.
In 1999, the physical assault on the Alps began. The miners prepared to plunge deep into the dark, unknowns. To achieve millimeter precision, Swiss surveyors had to link mountain base stations directly to global GPS satellite constellations. The geological core samples sent back a terrifying warning. The tunnel route would cross unstable fault zones, highly fractured.
At its deepest point, the tunnel would run under a staggering 2,300 meters of solid rock.
Miners entered the mountain through a massive vertical shaft at Sedrun, descending over 800 meters down into the heart of the Alps. Every foot they descended, the air became warmer and more humid. The water began to seep through the rock fissures, a constant warning of the mountain weighing down above. To coordinate the drilling from both Erstfeld and Bodio, the project used high-precision laser alignment networks. Standardized, heavy-duty American and European equipment was customized to withstand the extreme under-mountain humidity and abrasive granite dust. But the mountain fought back. The unstable geology triggered landslide risks and rock deformation, threatening to twist steel arches and bury excavators. The geodetic baselines were verified. The miners prepared to plunge deep. To excavate millions of tons of hard rock, the Swiss deployed 4 colossal Herrenknecht tunnel boring machines, each over 400 meters long and weighing 3,000 tons. But the Alps were unforgiving. The extreme rock pressure squeezed the tunnels, clamping the massive cutter heads and trapping the multi-million-dollar TBMs. The moving clay geological faults squeezed the machines like a vice, locking the cutter heads and trapping the TBMs. Engineers realized that machines could not conquer the mountains alone. They had to return to traditional, high-risk manual blasting and hand-shield mining.
Every day, workers loaded tons of dynamite into thousands of drill holes. The mountain beneath the Alps was systematic.
With a single throw of an electrical switch, millions of pounds of dynamite blasted the mountainside, unleashing a roaring shockwave that could be felt for miles.
The key to the excavation was speed. The railway conveyor belt had to move the debris out of the cut as fast as the shovels could dig.
But the mountain fought back. The unstable geology of Switzerland triggered catastrophic landslides. Entire nations.
By late 2003, despite the failures of the massive boring machines, the pilot tunnel dug from both sides.
The deeper they dug, the more dangerous the geologic conditions became. In May 2004, the pilot tunnel reached. At first, it was a whisper, a tiny stream of highly pressurized water hissing through the rock fissures under over 3 megapascals of crushing pressure.
The flooding was catastrophic.
The only line of defense was the massive steel bulkhead gates. Despite weighing several tons, these gates had to be closed manually against the extreme force of the water. The entire dewatering system was pushed to its absolute limit. High-capacity centrifugal dewatering pumps were activated, fighting to empty the flooded chambers. To consolidate the unstable, sugar-like dolomite, engineers developed high-pressure chemical grouting fragments. In severe squeezing rock zones, engineers installed innovative yielding steel arches. These arches were essentials. Every geological shift was monitored. Over time, the geomechanical curves flattened, proving that the active support system had
By late 2004, the impossible geological blockade had been broken.
Deep beneath the Alps, surveyors operated with blind precision. Using high-precision gyro compasses, they guided the excavation from opposite ends of the mountain.
By October 2010, only a thin wall of rock separated the two excavation headings.
With a single electrical command, the final barrier was shattered, sending a thundering shockwave through the 57-kilometer mountain corridor. As the dust settled, history was made. Two separate construction armies met deep inside the mountain core, completing the longest rail tunnel on Earth.
The historic Handshake united two nations and a continent. Under the Alps,
the final geodetic audit verified a miracle of precision. Over 57 kilometers of blind drilling, the two...
With the breakthrough complete, track installation commenced. High-precision paving machines laid a solid slab track foundation.
A giant steel shuttering jumbo worked continuously, pouring millions of cubic yards of concrete to form the secondary lining. The twin-tube layout was complete. Two independent concrete-lined tunnels stood ready to handle high-speed traffic, a masterpiece of subterranean infrastructure. Finally, the overhead catenary lines were installed. High-tensile copper wire was tensioned to feed 25,000 volts of electricity to the high-speed trains.
On June 1, 2016, the Gotthard Base Tunnel was officially opened, a new epoch of high-speed transit. The tunnel immediately transformed, allowing massive cargo trains weighing up to 4,000 tons to...
The Alpine blockade was conquered. High-speed rail slashed travel times across the mountain route, connecting northern and southern Europe.
The tunnel became the central heart of the Rhine-Alps corridor, redefining European logistics by shifting cargo from...
The entire network is managed from a centralized control center at Poligio. Every train movement, airflow rate, and energy parameter is monitored in real time.
The ultimate victory belonged to the thousands of miners who had fought the rock, the heat, and the water.
The Alpine giant entered operational history, a testament to what humanity can achieve when it dares to challenge the geological limits of the planet. At speeds of 250 kilometers per hour, trains act like giant pistons, compressing the air ahead and generating violent aerodynamic shockwaves. To dissipate this dangerous pressure, engineers constructed cross passages equipped with active aerodynamic dampers, venting the shockwaves into the adjacent tube. Under real-time computerized control, these dampers adjust dynamically, preventing concrete fatigue and protecting the structure from constant pressure cycles.
Deep inside the mountain, the project engineered Matis.
These stations are equipped with colossal axial fans, designed to extract toxic smoke and pump fresh air.
Supervisors continuously monitor the tunnel's vitals, using advanced telemetry to audit wind velocity, carbon monoxide, and humidity levels across the entire grid.
Over 57 kilometers of concrete lining are monitored by an embedded network of fiber optic sensors, detecting microfractures and structural strain under the mountain's weight. Even the barometric pressure wave output at the portals is monitored constantly, verifying that surrounding mountain villages are protected from the sonic booms of exiting trains. Millions of gallons of natural mountain seepage are captured and channeled away through advanced gravity drainage networks, protecting the rails and electronics from mineral corrosion, standing as definitive proof that when sharp journalistic vision meets peak engineering, humanity can rewrite the rules of its engagement with nature.